In this video I'll be talking about order stars. Now order stars are related to stability and the concept of relative stability. Now we've looked at the concept of absolute stability, and what we used is this test equation here, which is the first order ODE, so y dash equals lambda y, and we use that to analyse the stability of any ODE solver. Now the solution to this is e to the lambda t. So as t gets larger, the solution will grow exponentially. If the solution grows exponentially, well, so also will the errors. Now an ODE solver will remain stable if the errors grow at a rate less than the solution. So with absolute stability, we always ensured, or we needed to ensure, that the modulus of the stability function Rz was less than or equal to 1. So that ensured that errors did not grow over each time step. But with relative stability, we acknowledge that for the test equation, our solution is exponential, so the errors could be greater, or the growth in the errors could be greater than 1, yet the method would still remain stable. So this is the idea of relative stability. So the region of relative stability is defined as here. So Z is some complex number. Now Rz is the stability function, which was mentioned in a previous video. So the modulus of Rz has got to be less than or equal to the modulus of e to the z. So this is that concept where the errors can grow at a rate less than e to the z. Alternatively, we could write it like this. So we divide the stability function Rz by e to z, and we look for the value of this is less than or equal to 1. So where this value, Rz over e to z, or the modulus of that value is less than or equal to 1, we have relative stability, and our methods will still remain stable. Okay, with relative stability, we can plot the regions of relative stability, which gives us a concept of an order star. So for the second and fourth order explicit Runge-Kutta methods, we've seen in the past, but our stability function is the series expansion of e to the z. So for the second order Runge-Kutta method, RK2, we have the series expansion of e to the z up to order 2, and for the fourth order we have the expansion of e to the z up to order 4. So what I'm going to do now is plot the region of relative stability for both of these methods, and these are known as order stars. Okay, so here's the order star of the RK2 method. So at the moment it doesn't look too much like a star. The name order star was given because as we look at higher order methods, they start to have a star shape pattern. Okay, and with the fourth order Runge-Kutta method, you can see we got some characteristic type fingers coming out from the origin. Okay, so those are what order stars are. They're simply the plot of the region of relative stability. Another way to think about the order stars is this will be a surface, and we're taking a slice at the level of where the surface is equal to 1. So imagine this is a horizontal slice across that surface. Okay, a couple of notable features. We can split our order star into three kind of regions. We have A minus. Now this is a region where our the modulus of the stability function is less than that of e to the z. Okay, so this is the white region here. So where you see the white region, that's where our method is relatively stable. A naught is where it's equal, so the black border between the blue and the white regions is where we have our Rz is equal to Ez, and the shaded regions, the blue regions, are when we have Rz is greater than Ez. Now order stars, the reason they're of use to us is they're very easy to determine the order of a method and also some stability properties of a method. Now one property of an order star is that an order P method has P plus 1 shaded regions converging at the origin. So here I've got the order star for the fourth order Runge-Kutta method, and if we take a circle close to the origin, and as we trace it around, we enter 5 shaded regions. So we've got 1, 2, 3, 4, 5. So if we set up here, the order star of a pth order method has p plus 1 shaded regions, so if we subtract 1 from 5 we obviously get 4, so this represents a 4th order Runge-Kutta method. Okay, also another property of order stars is it allows us to quickly determine whether a method is astable or not. Now the definition of astability is that the region of absolute stability covers the whole left hand side of the complex plane. So what that means is there's no limit to the value of the step length h for our method to remain stable. Now the stability function Rz is equal to some polynomial function pz over another polynomial function qz, and we have 2 criterion for which determines whether a method is astable or not. Criterion A means all the poles are in the right hand plane, right hand side of the complex plane, so all poles of the method or of Q are in the right hand side of the complex plane. And we also have this criterion, so we define a function EY, which is given here, and if this is greater than or equal to 0, that means we have an or criterion B is satisfied. So if both A and B are satisfied, it means we have an astable method. Now the problem is with criterion B. Criterion A is quite easy to find. We simply find the roots of Q, and if they got positive real values, that's criterion A satisfied. Criterion B does require some quite complex algebra in places. So what we can do is, using an order star, we can replace criterion B here with this. So this means the shaded region, which is, remember, that's A plus, the intersection of the shaded region, I'll just go back, so this means this blue region here, the intersection with that with the imaginary axis is equal to the empty set. So in other words, the shaded region does not cross the imaginary axes. Okay, so if I go back to, this is the 4th order Runge-Kutta method order star, you can see down here and up here we have the shaded region crossing the imaginary axis, so this is not an astable method. Okay, at times the stability function, especially for implicit Runge-Kutta methods, can be complicated to determine. So what I'm going to do now is introduce the idea of Pardee approximants. Now a Pardee approximant is a function, it's a polynomial function, and it has a function on the top, I'm going to call it p of x, and a function on the bottom q of x. Now the polynomial function on the top has order L, and the function on the bottom q has order m. Okay, so this is an approximant of some other function, and we call this RLM. So RLM means the polynomial on the top has order L, and the polynomial on the bottom has order m. So if we want to approximate some function, say f of x, by a Pardee approximant, we have this following. So f of x equals the p of x over q of x. Now we want to satisfy this up to order L plus m. So in other words, if I set x equal to 0, we have the f of 0 must equal r of 0. Okay. The first derivative must equal to the first derivative, and second derivative must equal to the second derivative, all the way up to the L plus mth derivative must equal the L plus mth derivative of r. So the L plus mth derivative of f must be equal to L plus mth derivative of r. So what we can write is, if we subtract our approximant, which is, this is our Pardee approximant, RLMX, from f of x, we're going to have some error, because remember, this is only an approximant, but the error is going to be of order L plus m plus 1. So this means that RLM is an approximant of order L plus m of f of x. So I'll say that again. Our Pardee approximant L plus m is equivalent to f of x, or the approximation of f of x, up to order L plus m. So the Pardee approximants are useful because it allows us to approximate a function using lower order polynomials, or one lower order polynomial divided by another. So what we do is, if I go back a slide, so we have some polynomial function with coefficients a on the top, on the numerator, and another polynomial function with coefficient b on the denominator. We also ensure that b0, so when I equals 0, we say that b0 is equal to 1. So if we have some function, I've expanded out some function up to order L plus m, so here we have c are the coefficients of our series expansion of that function. That's the Pardee approximant is equal to the polynomial function p, which has a coefficients, and the polynomial function q, which has b coefficients, and we also set b0 to be equal to 1. Okay, so if we multiply both sides by this denominator here, we end up with a set of equations. So I'll just go back a sec. Okay, so multiply both sides by the denominator. So and then I'm gonna equate the coefficients of x to the power 0, x squared, x cubed, etc. So if we do that, we end up with a set of equations. Now the values of c are known. Okay, so c3, c2, c1, c0 here are all known. So we have a system of L plus m plus 1 equations and the same number of unknowns a and b. So we simply solve for that system. Once you've got a and b, you have your Pardee approximant. So let's have a look at an example. So we're going to have a look at the example of the Pardee approximant of exponential function of x of order L is 1 and m is 2. Okay, so this will give us a third order approximation of e to the x. Now L is 1 and m is 2, so on the left hand side I have the third order series expansion of e to the x. Okay, on the right hand side, because L is 1, I've got a first order polynomial with a0 and a1 of the coefficients, and on the bottom, because m is 2, I have a second order polynomial with, remember b0 is always 1, and we have b1 and b2 coefficients. If I multiply both sides by this denominator, okay, so we have 1, so that's a coefficient of x to the power 0. I've got 1 plus b1 times x, I've got a half plus b1 plus b2 times x squared, and I've got 1/6 plus a half b1 plus b2 times x cubed. So if we equate the coefficient of x on the left hand side is 1 and x on the right hand side is a0, so we know that a0 is equal to 1. The coefficient of x on the left hand side is 1 plus b1, and the coefficient of x on the right hand side is a1, so I know that a1 equals 1 plus b1. Now the coefficient of x on the coefficient of x squared on the left hand side is a half plus b1 plus b2, and the coefficient of x on the right hand side is 0. And similar for the coefficient of x cubed. So here we have 4 equations, and our unknowns are a0, a1, b1 and b2. So we can solve this, it's a linear system of equations for a and b. So the solution to this system, if you solve it, gives a1 is 1, a0 is 1, a1 is a third, b1 is minus 2/3, and b2 is 1/6. So the Pardee approximant is a0, which is 1, plus a1 times x, which is the third, and on the denominator I have 1 minus b1, or 1 plus b1, which is minus 2/3 times x, plus b2, which is 1/6 times x squared. So this is the Pardee approximant of e to the x of order 1, 2. Now what I've done here is I've tabulated some other Pardee approximants. So you have on the top, these are the order of the L, so these are the order of the numerator, and down on the left hand side here, this is order m, so this is the order of the denominator. Now these are all stability functions for Runge-Kutta methods. When m is 0, we have the first line. These are all stability functions for explicit methods. And when m is greater than 0, we have stability function for various implicit methods. And now it has been shown that when m minus l is between 0 and 2, we have an astable method. So that means all the methods on the main diagonal and the two lower diagonals are astable. So let's have a look at a few examples. So here we have L equals 2 and M equals 1. So this is an explicit method and it's a second order explicit method. So you can see it's second order because if I count the number of shaded regions around the origin, we have 3, so we know it's second order. Okay, here we have L equals 2 and M equals 2. Now this is 1, 2, 3, 4, 5. This is a fourth order method. Okay, and furthermore about this fourth order method, what are these dots here? These are the poles, or where our surface is asymptotic. These are both in the right hand plane, and this shaded blue region does not cross the imaginary axis. So it may look like it crosses here, but remember this is the A0, so the black border between the shaded and unshaded region is the A0 region. Now the criterion B for astability was that the A plus region didn't cross the imaginary axis. So this is an astable method. Okay, so here's the order star for a method which is a 2-3 approximant of e to the z. So I'm just going to count 1, 2, 3, 4, 5, 6. So this is a fifth order method. Okay, so there's 6 shaded regions surrounding the origin, and furthermore this is astable. Okay, so we can see, but the blue region does not cross over the imaginary axes. And if we go to the higher order still, so here we've got 1, 2, 3, 4, 5, 6, 7, 8. So this is a 7th order explicit Runge-Kutta method. Okay, but what we have here is the shaded regions do cross the imaginary axes, so this isn't an astable method. So these Pardee approximates are very useful because they allow us to tell whether, along with the order stars, whether we have astable implicit Runge-Kutta methods or not.